find symmetry without plotting for symmetry. There are simple tests that you can do with ordered pairs or with the actual equation to look for it. And they're really, really easy to use. For example, you have 3 different ways of symmetry that we're going to look at. We're going to look at the x-axis symmetry, y-axis symmetry, and symmetry through the origin. Let me go grab that. We'll be right back. Nobody's thinking about this. So what happens here is I want you to notice, look at the ordered pairs. When you have the ordered pairs, when you're symmetrical about the y-axis, what changes is just the sign of the x-coordinate, because it just flips over to the other side. When it's symmetrical about the x-axis, the only thing that changes is the y-coordinate. Those things flip. And then when it changes across the origin, both signs change. That's how it flips the other direction. And we're going to stay from the top. We're going to hang on the wall. Okay? So it's something that you guys have all seen, something you guys... It's something that you guys have all done. It's something you guys have all seen. You might not have... I don't think in algebra 2 most of you guys spend a lot of time dealing with symmetry as far as how the origin works and all that stuff. But I do know that you worked through it with the quadratics. That was very, very common. Okay? What will happen though is that we're going to be able to take the idea that you can use it's very simple there. That we can test an equation, or we can test sets of ordered pairs just to see if they're symmetrical from a list. And all you have to do is just look at how they correspond to one another. It's something that's really quite simple to do. It just has a lot of words thrown at it for the process to do it. That's all. So, in order to test, let me move this up here. X-axis. I'll leave it like that so we know what the curve might look like if it is like that. Let's see, what was it? X, Y, and then it implied that it was X, negative Y. Pretty easy. Y-axis. We had X, Y. Oops. And then we had change the x, keep the y. And then origin. Start with the x, y, and just exchange it. So what we're going to do, and these are the simple tests that I just have up there. It's the exact same things. It's symmetrical on the x-axis if you flip the points and they still wind up on the graph. Basically, if you change the sign of one of them and you substitute in the equation, if it still holds true, it works. All right? If you want to look at it, if I look at it with something that's easy, think about the graph of y equals x squared minus 2. We all know that's a parabola that starts at -2 on the y-axis, right? So if I have just a very simple set of ordered pairs, we know it would be at 0, -2, it would be at 1, -1, and -1, -1. What happens here is that if you know that 1, -1 is on there, Anyway, if you know that 1, -1 is on that graph, what you're checking here is, does -1, -1 work? All you're doing is substituting in. Does -1 equal -1 squared minus 2? Is that a true or a false statement? What's -1 squared? What's 1 minus 2? Is that a true statement? That's what that means, guys. That's all it is. You're just checking to see if it fits on the graph. If it lands on the graph, it works. And in order for something to land on the graph, it means that the equation, oops, sorry, I moved that up, guys. The equation holds true. That's all. It's just a quick little test that you do. There's nothing really out of the ordinary to do this. The other way that we can do these things is, no, I just did that. Got ahead of myself. Is to use it algebraically. And this is the newer one. This is the one that looks a little bit weird. When we test something algebraically, if we want to see if something's symmetrical with respect to the x-axis, which means this, if you replace y with the opposite of y, and the equations are the same. When you do that with the x-axis, you just change the x to the opposite of x, and the equations wind up being the same. Like I said, this looks weird, but when I show you an actual example, you'll be like, oh, that's all you have to do? It's okay, you don't have to snarl. Same idea with the last one. If you're going to check to see if it's symmetrical about the origin, if you replace the x and the y in the generic equation with opposite of x, opposite of y, or just use the negative symbols, and it simplifies out to do the exact same thing, then that works. It just all falls back into the idea of the x-axis, if you change the y's. Y-axis, change the x. Origin, change them both. That's all you gotta remember. Both, because there's an O in it. And then it's just the opposites. Does that make sense? I try to think of an easy way to remember it. Let me show you an algebra problem with this thing. I want to check, well, let's do this. I want to see how is this symmetrical? Or if at all. So if I want to check to see if that's symmetrical, what I'm going to do is do these tests. Do those tests for symmetry. And it's nothing more than going through the equations themselves and just switching values to see what works. Okay? Since I have a squared term here, and it's a negative squared term, I'm just going to move it to the other side. And just put that on one side and have the other, just an equivalent statement. So I get x minus 1 y squared. Is that okay?
Yes.
When I do that, I'm not changing anything. I'm just going to be less likely to screw something up with this sign. That's all. So now what I'm doing, I'm going to test the x-axis. So if I test the x-axis, what do I have to change? The y. So here's what I do. If I'm going to test the x-axis, I have the same x value. Will that equal negative y squared? What's negative y squared? Positive y squared. So isn't this the same? Therefore, it's symmetrical about what axis? The x-axis. That's what you're doing. You're checking it real quick. If I go to the other one, just to show you how it doesn't work, you test the y. Is negative x minus 1 equal to y squared the same as x minus 1? No. There's nothing I can do about it. So I know it won't work. Does that make sense? And then I know for certain if this one, if the y-axis one doesn't work, then I know for certain that the origin won't work. Because since I flipped the x values, it didn't give me a true statement. That means if I do it again, it's still not going to work. That's a little shortcut there. Does that make sense how I'm saying that? If you get a false on one of them, that means it probably ain't going to work on the other, on the last one. Okay? Remember, if there's a function that's symmetrical about all, circle. That's about all I can think of. Okay? Let's try another one. Let's try this one. Can I flip another one? Or is it still right now? Oh, sorry, it's minus x squared. And I want to see if it's how is this going to be symmetrical, if at all. So I just test them. Test at the x. When I test that, I just change the sign. By manipulating this, by moving things to other sides and all that, will I ever get a valid statement? No. I know it's not going to work. What do you mean?
If you say,
You're a step ahead of me. All I did, I just started with the x-axis first. Then I know that one won't work, so now I'm going to test the y-axis. And you're right. When I do the y-axis, when you square a negative x, you're going to be okay. When you fourth power that one, you're going to be okay. You're just a step ahead. Okay? So we know that this is a big old no. So when I test the y-axis, I change the x's. Well, y equals negative x to the fourth, oops, sorry about that, x, minus negative x squared plus 3. And just like he said a second ago, when you have a negative value raised to an even power, what will always happen? The value is positive. Very good. So no matter what the value of x is, winds up being, if it's negative and it's raised to an even power, it always becomes positive. So in this case, you do get a true statement. It doesn't change anything. So I know that no matter what, it's that. And if I go back again, and if I wanted to test the origin, since this yielded the same on the one side, and I know if I change that one, it won't work, I know it's not about the origin. So like I said, this looks a lot tougher than it really needs to be. All you're doing is just flipping signs. That's it. Okay? All we have to do is just flip some signs around and retest it. Want to try another one like that? Nice one.
Wait, can you do an origin? Or is there?
Oh, I'm sure there's an origin, but I just trying to find one off the top of my head. Is there one over there? Let's not get everything away.
Also now we don't have to do number 27?
We can do it now. Here's 27. If I'm testing this one to see where it's symmetrical, I start with the x, I check the x-axis. Well, is the opposite of y going to equal x cubed? It's kind of tough to tell, isn't it? Because of the odd power. I guess won't that be dependent upon the x? Yeah, so this one's, it's kind of weird when you start to think about it. Because it really depends if the x is odd or x is even, or x is positive or negative. Same idea if you go the other way. If you go y-axis, will y equal? It depends. See how there's a little gray area on that? It depends. There's such a dependency on what is the value you wind up substituting in for your ordered pairs. I would say iffy because I don't know yet. But now when I go to the last one, if I go to the origin, does the opposite of y equal x cubed? Is it this the exact same thing as? What happens here is that no matter what,
Wait, is there an inverse?
yeah, in the x, sorry. If I change these things through, if I change those things through, if I take ordered pairs, pick a value of x to generate a y, 2. 2 cubed is 8. Okay? Negative 2 cubed is negative 8. If I take those ordered pairs, 2, 8, and change both of those signs, it's still a valid thing. They both fall into place. Whereas if I take 2, it's 8. Is it negative 8? Only if it was negative 2. See how it's really dependent upon what value you choose. Whereas if you pick any value, 2, 8, 2 cubed is 8, negative 2 cubed is negative 8. Therefore, they fits for both of them at the same time. It's kind of weird when you start looking at the origin ones. And to be honest, it's usually odd power that works. Because when you look at those curves, they come up through the origin and then shift themselves out. Once you start stacking on the constants, you're adding on your plus c's and things like that. That's when things tend to move and shift around. That's when some of the symmetry doesn't work as clean, especially through the origin. It'll work through the axis because you can go up and down for the parabolas or left and right with the sideways parabola. But I know you guys have all done symmetry before. The other one that was in here that it asks you to remember how to graph was absolute value. Do you remember this vaguely from last year? Wait, you know what? I don't think we ever did absolute value last year, did we? No.
Wait, is it?
It is.
It's like a curve.
It is. It is. Absolute value is linear. It is a curve.
No, no.
It's not a curve. It is a line. Thank you. What happens with absolute value is usually taught, and I think last year we got rid of it, as the very first thing that introduced you to h's and k's. Where h and k was your center, the horizontal or vertical shift to something, and then you just walk the a value. I know there's no k in vertical, but it sounds cool.
Oh, I get it. But there's a C.
Correct, but there's no c in this.
Oh, I like
When you first learned this one, if you did or did not, it's not a big deal. This h and k helps you figure out where the change is going to occur at. So in this problem here, I have an h value of 6. I have no k value, which means that it's at 6 and 0. So if I graph this, it goes right there. The a value is some number that's out in front of the absolute value sign. In that case, it's what? It's 1. Now, this a value, treat that as a slope. Correct. Now, when I'm saying about treating it like a slope, I should probably put a piece of graphic right here. I'll give you guys a piece of graphic work, so you have to do some graphs tonight. When I'm saying treat this like a slope, is a positive or negative in this case? It's positive, which means it's going to open upward. Okay? Whenever I'm talking about this a value, I'm always thinking about it in terms of slope for the right hand of the absolute value graph, because that one has a positive slope of 1. And for it to be symmetrical, I just have to go the opposite of that, a slope of -1. And that's how that works. Okay? Just like we did with circles. Just like we did with the circles. Oh, I thought it was still up here. If you had the, you know, it was x plus 2 quantity squared plus y minus 1 quantity squared was 16. We knew that the center was located at -2 and 1. Because this was an x minus h, this was an x minus k. So it's whatever the h value is, and whatever, it's the opposite of the sign that you see here. So if it's -6, it means it's a positive 6. And if it was a +6, it would have been at -6. That's all. If it was x plus 6, excuse me, then I knew that the h value is -6. Because here I'd say this is x minus a -2. So
Yeah.
that's what I meant. All right. So the absolute value is symmetrical. It's symmetric about some vertical line. It's that vertical line that goes through the origin. It's the h value. Okay. I'm pretty sure you've seen that before. You might have just forgotten. Questions? Finish. Whatever it was, I think there's only, what, like 6 problems left on that assignment, I think? Yeah. Is that all it's left? That's it? Yeah.
But you don't need to sign for it.
47 every third and 42.
That's it?
I think you should keep it like that.
That's fine, we can do that, that's fine. Let's finish those out. Tomorrow and Tuesday is another big section of just so much review. Equations of lines, parallel perpendicular lines, writing equations, given 2 points, writing equations of line, given the slope, all that stuff. It's very, 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 very review.